on that? Okay, you guys, real quickly, just to start here today, with the sheets that you have in front of you, you guys know one's your normal format of notes, right? Okay. Then in front of you, you've got the two sheets. Now, were there two sheets there? The one that said exploration on it, and I think that there's two sheets. How many total explorations are there? There should be a total of, I think, 3 of them, right? Okay. So, listen, guys, we're going to start working on a new section. It's going to deal with some exponentials again, like we dealt with in the last section with radical functions and rational exponents. There's going to be some new concepts that come up. And first thing we're going to start dealing with today, kids, is this idea of, what's my title up here? Natural base of what? E. Now, as we start looking at this right here, it turns out mathematically E has some importance to it. It's some value that shows up often, and we're going to show you where it shows up. But first of all, we want to understand why it is what it is first today, okay? And we're going to look at some explorations that allow us to come up with that value, so I don't just say, E is this number, just accept it. I want you to understand why it is that way, okay? That's the first thing, all right? But here's the good part about this. Before we get into where we apply this type of stuff, we're going to ask ourselves the following question. What is our question here, kids, first? What is the natural base E? I'm going to read this. You guys follow along quickly. It says, so far in your math study, you have worked with special types of numbers such as pi, relative to what shape? Circles. Is pi rational or irrational? Irrational. And how about this value? I, which stands for what type of roots? Imaginary roots surfaced when we dealt with parabolas. And we call parabolas what type of functions? Quadratics. Very good. Okay. Hey, did you hear what I said to pi? P. Be rational. You know what pi said back to I? Get real. Alright. So we've got special numbers mathematically we talk about. Pi and I, we're familiar with those, okay? So today another special number is called the natural base. And that number is denoted by actually lowercase e. And that natural base e is what type of number again, kids? So you cannot find its exact value, okay? So the first thing that we want to look at doing today is where does this value of e come from, all right? How did we even come up with this, all right? And so on those pages that are titled explorations for you today, I'm going to divide you up, all right? So Audrey, your row, you guys are going to group together. I want you guys to look at exploration 1, okay? Talk about it, see if you can handle what's asked there in this exploration. If you need any help with it, yell at me. I'll be around, okay? You guys group together. This row right here, guess what exploration you're going to get to do? Number 2. So I want you guys to group together. Or if you want to pair up right now first, talk about them, and then get together as a whole group. You guys are going to share out here in about 3 minutes or so. And then you kids and Alta, you guys are going to do exploration number 3 right now, okay? I would suggest for you guys either a calculator or maybe decimals as you go through that when you're working on it, okay? So take a couple minutes, look at what the exploration parts say. We're going to share out on that in a second, and we'll see where we're at with that, okay? Sound good? Audrey, what are you in charge of?
Hey guys.
1. You guys, 2 and 3. Okay, so see what you've got here.
Exploration.
Now give about 3 to 4 minutes on this, all right?
Okay. So, or one way to approximate the natural base e is to approximate the sum. Use a spreadsheet or graphic calculator to approximate the sum. Display the steps in use.
Okay,
How many
big
decimal
idea is
places to
not
do an approximation. So we're just basically adding them up.
on your graphs right here. I really want to draw X and Y axis and both numbers.
Wait, there's a dot here.
Guys, I'm going to tell you, really all you're doing
Yeah.
is evaluating these tables. So I'm seeing what e to the negative 2 power. So what I'm asking you now is you can figure out where the button is. The button you can calculate, and then you're going to help me with other kids do that, okay? You guys got that? Okay. Any questions about what you're looking at so far?
It's, yeah, because it's an approximation, so.
So then I just put.
Well, the value, they don't care about this, yep, so, why don't you guys share out to about 4 places? I don't think it says. So in his calculator, he uses decimals, so you use the same thing. Is that a match? Okay, you guys on task then? Questions at all? You only chip in, right?
Yeah.
Oh, so maybe we shouldn't even write it. How we-
Oh, yeah, it's not
You
enough.
got the,
Easiest
I
one.
just love, we were using our calculators, so.
okay, here's the deal.
Oh, yeah, we can just.
As long as we're able to do all 4 of those, then
Or I
you're
can
good
just
to
tell
go.
you.
Okay,
I
so
would say
you're just
type
gonna
in
put some
exactly
decisions.
like this. I don't really care.
Wait, it's like
I don't like
Oh,
the
you
Yeah, I
can do
know.
your
Just gonna put 10 on it.
like 3
So you can put on and on, so.
Well, whatever
do you know this-
364,180 times.
Well, we could put.
10. Oh, that's easy.
Because we've got to
Yeah, I was gonna say, that's the easiest one.
3,641,800.
Then what? Is it our sum?
You want me to take 3 million something? Well, no, because all these are 1 over.
Yeah.
Okay. Who else has a calculator? I'll punch those in.
So I think we need to put this in decimals, right?
Not necessarily.
No, I just,
So, what's this say right here? for you guys?
It's just the opposite, so it'd be like 2.
2.593.
It just writes like.
So, okay, so they're saying type 1 is 1
Plus
over,
1.
plus 1 over,
It's the opposite, so it actually
plus
has
1
so
over.
2.5.
And so just don't even bank them right now, let's just talk about the process first.
okay, so I'm just adding.
Okay, now what does this dot mean?
Continue.
It goes on forever. You guys remember when we okay, factorials, that's great, you're gonna bring that up. So, yeah, maybe you guys add like, okay, so what this is really becoming is like 1, that's that first one, plus 1 over 1 factorial, plus 1 over 2 factorial, because that's, okay, why don't you guys, here's what I would suggest for you. This dot means it goes on forever, but you're gonna notice something right about here, so I'm gonna say maybe go on 2 more places, so you might have 1 over 5 factorial plus 1 over, okay, so what I want you to maybe do then is this.
Should I just get a crumb?
I can help
Should I
you
get
with the first couple.
Cosmos and just put
I'm
X
gonna
equals?
say, just as approximate, so no problem. You know what this first one's gonna be put down. 1 plus
1 plus 1.
1, start turning stuff to decimals when you figure this out. Okay, and see what you get for a value, and you go, what do you guys wanna grade it out to? 1 over what factorial?
I just got it.
Oh, you wanna go 10, you're an overachiever.
I would say like
That's
6.
great,
Or
I love
5
your
or
idea,
6.
I love your idea, but you're gonna get some really small values that are gonna be hard to work with, I'd say 6 would be, right? See what you get a couple minutes, and then be ready to share out, okay?
Okay. Plus.
Great.
What?
Is that calculator work for you?
5 plus.
See what you end up with, 3 more?
Oh, the negative.
Wait, was that for 100?
It is, just like.
That was for,
Why?
that was for 1,000.
Because it's
The first one is.
Yeah, it's the opposite, so it's basically opposite negative 2.
Oh, yeah, we're right.
Yeah, so what do you notice about this table and this table?
Yeah,
Okay, so you guys are spot on right here, I'd like you to do that, assume every value or every change in the grid here is 1 unit.
Okay, so 10
Try to
is
plot your
for-
points here in this graph as best you can, plot your points in this graph, and then make your comparison about the 2 graphs, and then notice how, and
Oh, the 6 is repeated.
show me that.
Start showing these up.
And don't forget, remember, I want you guys to.
Okay,
look
so
at
it's
X, Y axis.
1 plus 1 plus 0.5 plus
0.718.
0.6 repeated plus 0.16 repeated.
You guys getting close?
Up around here.
100,000, okay.
What do you guys notice about those values as you have 1 over larger factorials? Really close to what value?
0.7.
So if I keep adding really small values, is this gonna grow a lot or kind of stall out somewhere?
2.718.
Should stall out, good Sarah.
It's getting closer to 8.
Okay. Yeah, we're good. Well, this one's 1, so that's second place.
My bad.
That's all right. So go ahead, you guys punch that up, see where you're at with that, right?
So that's gonna get you.
What do you guys notice?
That's getting closer to whatever.
The 8 should have been there because the 1, that doesn't have a factorial.
Did you type in 1 million?
0, 0,
Are you
1,
doing 1 million right now?
2.7183.
Good.
What?
Okay, I have an error in the summary. I got 1,390.
That's okay, we'll come together. Because that's kind of everybody share out. Nope, I think you're good shape, we'll talk about that.
You can see those numbers.
You've got what I want you to have right now. So you get this part, I want you to have it.
You can read those numbers? Can you see those numbers?
Hey, group 1, all good?
Yes.
Guys feel ready to talk?
Yes.
Group 2,
How do you read that?
feel good? Okay, group 3, you guys ready to talk?
Yep.
Okay. Hey, why don't you guys bring your attention to the front here then? So here's what we're gonna do. Sounds like all 3 of you got through your own explanation the way it was supposed to, or exploration as you were supposed to. And let's see, my group 1 right here. Audrey, Christian, May.
Are we going up in
No, I'm gonna have you kind of help me understand what's up here, but I want kind of your explanation in your own words as to what's going on here, okay? We talked about this idea. Our essential question again was what, kids?
What is the natural base?
What is the natural base E? Where does this thing even come from? Why is this irrational number talked about? We know about pi and we know about I, okay? So we're gonna add another one into our toolbox. So we're gonna talk about the number E, where it comes from, and eventually we'll get into why it's used and where it's used and look at some real life applications with this. But guys, the first exploration question up here is this. It said approximating the natural base E. Group 1, you were told to work with a partner. You guys did a great job. One way to approximate the natural base E is to approximate the following sum. Okay? What do you guys realize about that sum? Or what's unique about that sum?
They're factorials.
What's a factorial?
When you do like, if it's like 4 factorial, then you do 4 times 3 times 2 times 1.
Okay, so 4 all the way down to 1. All those values times 4, 3, 2, 1. So you recognize this. So you recognize this as 1 plus 1 over 1 factorial plus 1 over 2 factorial. And this just kept going. The pattern kept going. So my question is, I see this dot, dot, dot out here. How far did you guys go? Did you stop at 4 factorial or did you go a little further?
We went
We
to
went to
6.
So you added in, and you guys will want to write this down that don't have an example 1. It says one way to, what's the word again? Approximate. That's the only thing I can use because it's irrational. Approximate this value. They added in 1 over 5 factorial. Okay, remind me what that means again one more time.
5 times 4 times 3 times 2 times 1.
Exactly, okay? And then you said you went up to plus
1 over 6.
Okay, so I think that's probably a pretty good, stopping point to maybe approximate this. Down here it said use a spreadsheet. I don't know what you guys did, but it said use a spreadsheet, graphing calculator to approximate this sum. Explain the steps you used, and how many decimal places did you use in your approximation. So, looks like you went from 1 over 0 factorial to 1 over 6 factorial. I like these first values to work with. What's this going to equal?
1.
So this really becomes 1
1 plus 1.
plus, again, this one would be,
1.
okay, what's this going to be then, kids?
1.
Okay, and they've already punched the numbers in, so I'm going to put everything in decimal form. It's easier for me to work that way. What did you guys get for this? This is really 1/6, isn't it?
0.16 repeated.
Okay, how many places did you guys go in your final answer?
3.
So is it okay if I call this 0.167 maybe?
Yeah.
All right, how about this 1 over 4 factorial?
0, 1,
0.015, right?
Wait, what? Because we're going to 3 decimal places.
Okay, this was my first one. This was 1 over 1. This was the 1/2. This was the 1 over 3 factorial. 1 over 4 factorial.
And That's 4-1.
And,
Yeah.
1 second, it's 4-1.
so
Wait, I
this
thought you had
0.1 or 0.015 needs to be changed to what again?
0-1-4.
4.0
4-1.
But we're only doing 3 decimal places. Because our final answer is.
Pick a number.
5-4-1.
24, right?
So this one's 0.041, you say?
0.042.
42, all right. You guys all in agreement there?
6. 2.
Okay, yep.
Okay.
Okay.
And that was for the 4 factorial, 1 over 4 factorial. What was 1 over 5 factorial, kids?
0-0-8.
0.008.
Yep.
And how about 1 over 6 factorial?
0.001.
Now kids, like that there?
Uh-huh.
All right, I want to ask a few questions about this. As I continue to make these factorials in the denominator larger and larger and larger, what are these values getting closer and closer and closer to? 0. So eventually, these values are going to get so close to 0, it's essentially like adding nothing on the further we go, right? And that's going to give you an idea of a number stalling out somewhere. When you added that mess up right there, what did it get you?
2.718.
2.718. So they're saying one way to approximate the natural base E is to say E is approximately what value again, Sarah?
2.718.
Okay. Did anybody know that E was equal to 2.718 in the beginning?
After looking up there, yeah.
You've seen that poster up there before, right?
Yeah.
Never really paid any attention to it, but now if you look at it, 2.718. This is considered the natural base, E. 2.718, that's a pretty good approximation of that, okay? All right, groups 2 and 3. Have you got what you need from that exploration? How about groups 2 and 3? Any questions for group 1 right now? Solid explanation?
Yeah.
Thumbs up if you're okay with that. Good job, group 1. All right, let's move to group 2 then. Let's talk. Group 2, you had a pretty nice one to work with, I thought. This is one way to approximate the natural base of E. The second one that we're going to look at is going to be more mathematically correct. In fact, this is the actual definition of finding E, and I'll tell you why here when we get into the notes after this. But group 2 said another way to approximate the natural base E is to consider which expression? This one right here. 1 plus 1 over x to what power? X. And it says, and there's something very important down here, and I think that you should probably box this. I think that you should probably highlight this. I don't know. I think that what they say right here is very important, okay? This first sentence is very important. I'm gonna get a funny looking shape up there, but there's some important things happening there. Somebody in group 2, read that part that we just highlighted.
As x increases, the value of this expression approaches the value of
Okay, so we're saying x is always doing what?
What, closer to E?
Well, okay, so we're getting closer to E as x does what? Increases. And is x just going to be some small value, or is that going to continue to grow and grow and grow? It might tend towards what value? How much? 1 million. Or that guy over there might say we're going where? To infinity, right? Okay. So, yeah, this is really the actual definition of where E comes from. This expression 1 plus 1 over x is telling you as x increases, we're going to approach the value of E. And they say in this right here, complete the following table, then use the results in the table to approximate that. So guys, I see that they wrote these x values to get larger. They wrote these as bases of 10. I don't really like that. But really all you did is take this expression and do what with it? Put x in, okay? So in this first one, you would be putting a 10 in right over here. Okay, so you might have written this as 1. You guys tell me what you wrote. 1 plus what? Or what did you type into your calculator? I guess that's the better question. Say again, Megan.
1 over 10.
Okay. All to what power, kiddo?
10.
And it's a 10 right there, right? Now, I'm not gonna rewrite these all this way, but guys, when you punch that up, maybe, I don't know, how many places did you go over? One more. Okay, so what'd you get here? 2.5937. Okay? Then you did the same exact thing, and what did you put in for x next time?
100.
100, because 10 to the second is 100. What was your approximation there?
2.7048.
2.7048. Oh. What'd you put in next? 1,000. What do we end with there? 7169. What do we get here?
2.7181.
How about here?
2.7183.
Oh my gosh, what do we get over here?
2.7183.
Guys, where are we stalling out at?
Between 5 and 6.
Okay, between the fifth and sixth power, but what value do we eventually kind of close in on? If I had to go 3 places beyond the decimal, what would be a great approximation for your value E? 2.718, okay? I want to make a note up here, guys. E is approximated by this expression, 1 over 1 divided by x, all to the x power, as, what did we highlight right here, kids? X increases, as x approaches a place that he likes. Positive infinity, okay? This is crucial to understanding where E comes from, all right? Now again, there are gonna be a ton of applications for this, especially when we talk about compounding interest as it relates to loans. You'll see that application when we get into the notes, but give me a show of hands right now. How many understand at least where E comes from right now? And how many get that E is about 2.718 at this point, okay? All right, so rather than just start by saying, guys, E is 2.718, let's move on. Now you know why, right? All right. So, group 1 and group 3, any questions for group 2? Well done, kids, well done. All right, group 3. Group 3, I think you had maybe the most time-consuming one. Are you ready for me? Let me get to the next page. Group 3, who's gonna be your spokesperson?
I can do it.
All right. Who is I can do it? Is that Maddie or
Maddie,
Ellen?
yes.
Okay, give me a second here, kiddo. I told you guys on the graphs to do what?
To draw the y and x axis.
Okay, so you might want to sketch those in there real quickly if you haven't done so already. So here's your x-axis. Whoops, I better capture it first. All right, Pokemon Go capture. Let's roll. Any questions for me to this point? Okay. Maddie, what was your job in example 3 or exploration 3? Do you want to read that to the class so they know what you were trying to accomplish here?
Yes, so use your approximate value of E in exploration 1 or 2 to complete the table. Then sketch the graph of the natural base exponential function y equals e to the x power.
Okay.
You can use a graphing calculator or the key on your calculator to check the graph.
Okay, I guess my first question would be, does everybody have their calculator out right now? What, is there anybody, how many of you guys are using the TI-30 right now? Okay. I think if you hit the second button on that, and then, is there an LN button like 2?
Oh, yeah.
So if you hit second LN, it should kick out an E, it should raise it to a power. Does it put parentheses right after that?
Yeah.
That's excellent, all right? Now, the calculators I'm not familiar with, who needs help finding E in their calculator? Are we good?
E to the x.
All right. Your job, it says to me right here, Maddie, and if I understand your group correctly, you were supposed to put these values in for E to the x and get values out and then graph, is that right?
Yes.
Okay, tell me what you got when you want E to the -2 power.
We got 0.135.
Okay. 0.135. How about e to the negative 1? What'd you get there?
0.368.
As we've talked about, any base other than 0 to the 0 power would always equal 1. What'd you get for e to the 0?
1.
That makes sense. Guys, isn't x to the first just the same as x? When you punched in e to the first, what did it kick out?
Oh, it kicked out 2.718.
That's kind of important because what's the value of e that we've already discovered?
Right there.
2.718. So again, we've discovered it that way. All right, technology helps. What is it for e squared?
7.389.
7.389. All right. So I'm gonna do my best to sketch this. I would sketch these points, -2 comma what? So left 2, up maybe 0.135, maybe that's right about here, and this won't be the best sketch in the world, all right? -1, what's that? Oh, 0.4 maybe right here. 0 was at 1. 1 was almost up to 3, wasn't it? A little shy of that. And then 2 was up here, maybe about 7 point something. This is 5, 6, 7, almost 8. Guys, what kind of shape is that graph appear to be taking on right there?
Ooh.
What do they call that? What do they call that? That looks like my
Exponential.
credit card bill when my wife goes shopping.
Exponential. It's exponential.
Exponential, yeah. Hey, how about a better question, Christian? Is this exponential growth or decay, buddy?
Exponential growth.
Yeah. All right, now that's the best sketch I can give you, which is not too bad, but if we, I'll come back to this right here. I'll go into decimals and look at this more exactly, but do you understand these values right here? As x is increasing, what's happening to your y values? They are also increasing, right? So, I think we get that. I'm gonna make this go away for a second and go down to that second part. Groups 1 and 2, do you have this right now?
Yep.
Yes, Charlie.
Manny, somebody different in your group, what'd you guys find out about y equals e to the x and y equals e to the negative x?
It just flips.
What do you mean it just flips?
Like the 2 in the first one and -2 are the same thing, and 1 and -1 in the second one are the same thing.
So,
of course, the zeros are the same.
up here, when you had e to the x, when you had y equals e to the x,
It's just the opposite. So just opposite.
and your x value was over here at 2, what was your y value again? Was it 7 point?
Yeah, 7.389.
Well, now it's saying, let's suggest graphing y equals e to the negative x here, right? So when I throw -2 in here, if this already says the opposite of x, what's the opposite of that -2 gonna be?
+2.
Which was what value again from the previous problem?
Yeah, that one.
Yeah, you guys were spot on that. So this is gonna be a 7.839. Basically, it's the reverse order of that table, isn't it?
Yeah.
So what was next? E to the -1 should have been my,
It's 2.718. But yeah, it's your positive
okay, and then e to the 0 was,
1.
and then this was it point
136.
3?
135. 135. 135.
368.
Did I write it down wrong, the other one?
Yep, yep, negative.
What? What am I
Okay,
Oh, yeah, -2 is 389.
right here.
Yeah.
Oh, sorry, that was my
Well,
bad. I
that's
think
okay,
my
I'll get it. So what was that value right here again?
389.
Got another year older this week, I can't hear anymore. What was this down here, point?
135.
Okay, so now I asked you guys to graph the shape of that. I'm not gonna do that because I know you can plot the points in there. Make sure you have your XY axis in here. Kids, the thing that I really wanted to point out was this. Do you have the values in your first question? Okay, if I was graphing these y equals e to the x, I'm gonna go in here. Y equals e to the x. We've got it plotted up here already. Did that look like the first graph we got as an exponential function?
Yep.
Okay, all right. You said this was exponential what?
Exponential growth.
Growth. When I take that away, here's what e to the negative x those points would have plotted out to be. This is gonna be exponential decay. Basically, this is a reflection over which axis?
The y.
The y-axis, all right? Things to think about, and this is really what I want you to discover out of this, but they asked the question down there in number 6, kids. They say, how are these graphs related? Or how are they contrasted? What did you guys come up with as a group? I'm kind of looking at number, well, not really about 6. What I'm really concerned about is, it says number 5, right? Compare the graphs of them. What did you notice? We've kind of already told them. One is,
Exponential growth,
one is,
exponential decay.
okay, which is which? How do I differentiate that? How do I know?
The growth is going up to the right.
What if I didn't give you a graph? What if I said, hey, here's your 2 functions. How do I know which one's growth and how do I know which one's decay?
Because decay is always decreasing, and that's by the minus sign.
Okay. So if that variable that's an exponent here is positive, what type of exponential function will you have?
Growth.
And if that exponent is negative,
Decay.
then that's gonna be some kind of a decay situation. Okay, so in number 5, let's bring that together. What do you notice? One's growth, one's decay. You should write that down. One's growth, one is decay. And then the other part you should write is if your exponent is positive, it's what type?
Growth.
Positive exponents represent growth. What else could I say beyond that? Positive exponents represent growth. What else could I say beyond that?
Negative exponents equal.
Negative exponents are going to represent,
Decay.
say it again, Adam, for everybody.
Decay.
Negative exponents are going to represent decay. All good?
Yes.
All right. Couple things to round up, summarize before we start the new notes here. E is approximately what value?
2.71.
E is approximately 2.718. That comes from the following expression. 1 plus, anybody have it memorized?
1 over x to the x power.
As what happens?
As x increases.
As x increases, or we do mathematical sense, say x approaches infinity, okay? That's where that comes from, all right? Now, why the heck do we need to know about this? Well, I think if we take a look at our notes, look at what our essential question is again, look at the goals we're trying to identify, I think you'll see why we're gonna use this, all right? I have a question for you kids. How many of you guys like money? That's the one thing that we can all agree on, is that we all love money, right? And you know what the answer to this question is gonna be every single time? Can you ever have enough money? And we all know the answer to that is what? No. All right, we all want more, okay? Just because we have things that we like doesn't mean that we don't want more. Would you agree with that?
Yes, we do.
Okay. So, in today's world, kids, we start talking about stuff. How many of you guys have a savings account or maybe some kind of, okay. Now, how many of you guys have a savings account where your savings account from month to month goes from here to here to here to here?
Mine's like 10%.
Mine's,
Okay.
yeah.
I just do it.
All right. Here's what I think could happen, all right? Now, this would have to be a pretty high interest rate or something like this, but one thing that I think about a lot, and I'm way past the game, I missed the boat, or whatever you wanna say, is that when I started a family, when I had kids, I should have taken X amount of dollars and set it aside in a high yield market and let that money work for itself. In other words, what I'm saying is this. Let's just pretend, who can I pick on right now?
Me.
Adam, let's pick on you. Adam, let's just say that when you were born, how many years were you born? How old are you?
16.
16, all right. Adam, let's just say this. Let's just say maybe your parents said, you know what, Adam's born. You know, the day he was born, they created an account. They call it the Adam account. And they said, maybe, just maybe, we've got $3,000. We're just gonna jumpstart an account for him. You okay with that? Now, that $3,000 is all 100% of the $3,000. So if I wanted to multiply $3,000 by something and keep it the same, what would I multiply by? 1. Okay, so I'm gonna put this 1 in here. Now Adam, putting money in bank or in a high yield market, is gonna earn something by having that money in there. And what is it that he's gonna earn by just letting that money sit in there?
Interest.
What's that called? Interest, all right? Not like the interest you have in this class, but like the interest that you earn when your money's in some kind of a market, okay? Do banks give you a lot of interest on just a savings account? Not really. I think my dividend this month was 6 cents. But hey, that's 6 cents that I didn't have, right? And I didn't have to do anything for, all right? But here's the deal. If I want to make money, do I want my interest rate to be higher? When I put my money in the bank, do I want a higher interest rate or a lower interest rate if I'm going to make money? I want a high interest rate. On the flip of that, what if I was borrowing money? If you want a low interest rate, because you don't want to have to pay back too much extra from what you borrow. Agree with that? So you've got a lot of exposure to that in some of your other classes. Well, let's just pretend this. Adam, I'm going to pretend that maybe we found an account or maybe some kind of a market to put your money in that earns you, how about, I'm going to be nice today. I'm going to give you 12%.
Wow.
Now what's 12% going to look like as a decimal, kids?
0.12.
0.12. Now here's the deal. Have you guys in other classes talked about how often your money is compounded? Like certain time frames? Monthly.
Monthly.
That's another. I heard another one. What was another one?
Quarterly.
I hear quarterly. What's another? Semi-annually.
Annually.
Okay, so you know this stuff. Okay. Let me ask you this question: is it good to just compound your money once a year or multiple times during the year?
Multiple.
So, what do you want to pick? Should we do it every single? Let's get even better. Let's go every single day, because that days, how many days are in here?
66.
Oh my God, that 365, that number's getting to be pretty what? Big. X is approaching a big number. Oh, this concept of E is all of a sudden, what if I did it every hour? What if I did it every second?
I think that's a little extensive here.
Now wait a minute, we just talked about this because we said if we go on as X approaches infinity, kids, it starts to become what? Well, let's take that 12%. Let's just do daily. Should we do daily and see how much money he has after how many years? 16? Okay, your formula would look like this. You would take that 12% and divide it up over 365 days. But then you would raise that gets compounded every single day. So how many days? So you would raise that to the 365 power times how many years?
16.
Okay, I want to show you something here, kids. I want you to have your calculators out. I want everybody to punch this in just to understand this. Adam had, when he was born, $3,000 just put into an account that compounded at 12% daily. Do you know how much money that would be? Anyone might guess what that's worth right now? Just take a guess before you even punch it in.
Millions.
Who knows? I don't know what it is, but this is just going to give you an idea. Okay? Punch that in. See what you get. Make sure you punch it in exactly the way I have it written up here. So parentheses here, parentheses on your exponent for 365 times 16. Make sure a few of you, yep, the 3,000 goes in front because that's what we started with.
Wait, oh, times 16.
How much money did that make?
Oh no, I got syntax error.
What'd you get? 6.8?
$20,456.
How much?
$20,456.42.
Let me ask this question. What if you did this? What if you did this? Hypothetically, what if you did this? What if we said, you know what, it would really be nice to give Adam a nice graduation present. So let's turn 16 years into probably what? 18. Okay, do that for me. Get rid of the 16. Change this to 18 for me.
I keep getting seen right there.
Okay, I'm gonna come over and look at what you're typing in, all right?
26,000.
How much was it last time?
$4.18.
So I made $6,000 in 2 years.
Divided by.
Yeah.
Yeah, I'm trying to find by here.
Wow.
2 to 365 times 18.
There we go. It was just
Oh, yep, I was just, wow,
What do you guys get when you punch that up?
$26,004.
In 18 cents.
I'll take the 18 cents. Nothing's free. Here's the deal, and again, this is all speculative, okay, but it's possible. If I was, say, let's just scenario. Adam, I set $3,000 aside for you when you were born, and I put it in a market that earns 12% interest daily. By the time you graduate, that $3,000 that I was gonna give you at the beginning is how much money? So if you graduated and I said, here's your gift, $26,004.18, would you be pretty pumped?
Yeah.
Pretty good start in life, isn't it? Okay? This is an idea of how something small will start to grow very what? Very quickly. Okay? Very quickly.
That's compounded daily.
What if it was compounded continuously? You want to do continuously quick? We're going to run into that. You want to know what continuously looks like? Here's what continuously looks like. It's not going to be much different, but $3,000 times E, because E is my what value again? It's natural base. It's like my rate over something. As X gets very large, if we compound continuously, what rate were we at? 0.12, is that right?
Yeah.
Now again, I'm ahead of the game a little bit with you guys, and I'll show you why this works here in a second, but somebody punch that in. Go 3,000 times E to the 0.12 times 18.
$26,013.41.
26. Man, if we're making how much money, we've just solved the US deficit. Holy smokes. It's gotta be 0.12. Okay, that would mean that they're getting 1,200% interest. And if you ever find 1,200% interest, please let me know. I have a couple dollars I'll throw into that, all right? Okay. 26,000, how much?
$26,013.41.
So here's the deal. How many cents?
41.
Christian, when you punch those up, was there much of a difference between what we were getting monthly and what we get continuously? No, it would take a lot of time to really see some separation from that, okay? And again, you'll see when we start changing parameters with this stuff here, probably tomorrow now, why that is the way it is, but guys, there's so many accounting principles that come along with this natural number E, and things that have to do with populations that are growing over time. So I think what I want to do is I want to look at what we have going on first here in our notes, okay? So on the first page of notes there, let's just at least get through the vocab here before we end up taking off today. Okay. So we have an idea of what the natural base E is, and again, such a question is saying, what is this natural base E? So what are we looking to do here? What are we looking to establish, or what are we looking to accomplish here? Well, who's got the first one?
Define and use the natural base E.
We've kind of done that already, right? We already know where that comes from. Second thing, we've looked at some graphs of natural base functions. We'll look at some more. This is going to be the biggie right here. Looking at solving real life problems when it comes to natural base E. All right. So let's work hard to get through this vocabulary here. Natural base E. Who wants to read that for me?
The history of mathematics is marked by the discovery of special numbers such as pi and I. Another special number is denoted by the letter E. The number is called the natural base E. Expression 1 plus 1 over x to the x power approaches E as x increases.
It's a lot for a definition, but we kind of discovered already that, you know what, E is approximately, what value again?
2.718.
E is approximately 2.718. And it comes from this idea that E is approximately the expression, you got it memorized?
1 plus 1 over x to the x.
As what? That's what you really need to know there, okay? That's what you need to know right there. So that's great, you know that. Irrational number. Okay, and what type of number is E?
Irrational.
E is irrational, okay? Like what other famous irrational value?
Pi.
Exactly. E is irrational, right? Guys, we need to revisit properties of exponents again. There's a lot of writing, or I'm sorry, a lot of reading in that definition. I'm gonna kind of sum it up here the best I can. It says when you raise a quotient to a power, you raise both the numerator and what? Okay, I'm gonna kind of divide this up like so. Put a line right here. That's one part we're gonna talk about. It says when you raise a number to a 0 power, you'll always get what? I'm gonna put a line right there to kind of divide that up. Negative exponents are the reciprocals of the positive exponents. The same properties of exponents apply for both positive and negative exponents. I'll show you what these all mean in a nutshell. It says when you raise a quotient to a what? You raise both the numerator and the what? All this first one is saying is this: if I have A over B all to the nth power, that's going to equal, anybody want to guess?
A to the n over b to the n.
Very good. Okay. That's something we've talked about. We need to revisit that to make sure we're successful in this section. Okay. Next one says the following. When you raise a number to what power?
0.
0 power, you're going to get what?
1.
Okay. I'm going to say A to the 0 power is equal to 1, but A cannot equal what?
0.
0. We start doing that, the crazy stuff starts happening, right? So any number other than 0 to the 0 power is going to be 1. And then the last one says negative exponents are the reciprocals of positive exponents. I'm just going to make this relevant for both numerator and denominator. What this is really saying is this: if you had A over negative B and then X over negative Y, you guys remember what you do with the bases to make the negative exponents become positive exponents? Okay, so when you say flip them, what do you mean here, Adam? Okay, so that base, where if you have a base up here as a negative exponent up in the numerator, that same base would have what type of?
A positive exponent in the
Would have a positive exponent in the denominator. So what would this equal if I wrote this all with positive exponents?
X to the y over a to the b.
Very good. Okay. So these three rules that we just covered again, you've seen them. That's what this is saying. Properties of exponents, make sure you remember. Exponential growth, we kind of talked about that already. Is that an increasing function or decreasing function?
Increases.
Okay, so maybe make the sketch look like that. That's what most graphs of exponential growth are going to look like. I am going to throw a short formula up there because it's going to show up in some of this, but kids, if I'm going to show exponential growth, am I adding to what I started with or subtracting from what I started with? So you might see a function like this. You might say A, amount A is equal to some value you start with. They're going to call it principal times 1 plus a certain percentage rate to the t power. Okay. So if that's maybe a general formula for exponential growth, does anybody want to take a guess on what exponential decay might be?
There's no, not that low one.
Yeah.
6R.
Not, just leave it as is for now. Okay, just the R. We'll talk, when we start talking about things like, especially finances, loans, or calculating interest over certain time frames, then we'll have that n in there, and we'll get to that, okay? All right, exponential decay function looks like this. Same exact thing, but what? Yeah, we're not adding to what we originally started with, we're actually subtracting some percent from that, okay? So you want to know that, right? asymptote. I wanna,
We just talked about this in trig.
that's a great cross-curricular connection. What is an asymptote?
It's like an imaginary line on a graph where like it's not gonna hit.
You guys ever heard of Zeno's paradox? I'm quite sure I've done this for you before.
Yep, where you go halfway.
Yeah, if I start at this door and I want to go to that door and I say, hey, Parson, walk halfway to that door. Okay, and stop halfway there, right? And then they say, from that point, go to that door, but only go how far? Halfway. And stop. I wasn't telling you to stop, Grace. I'm sorry. And now I say, go halfway. How many of you guys want to watch me go halfway to the door for each time I stop? I'm going to go halfway.
Yeah, but it would get infinitely close.
Will I ever get there?
No.
We better get some popcorn. We're going to be here for a while.
You're only gonna get halfway there and start.
Yeah, well, I'll never get all the way there if I stop and then go halfway from where I am to the door, right? It means I get really, really close, but actually what happens? I never get there, okay? And that's exactly what an asymptote is. Maddie, it sounds like you're pretty pumped up about this. It's a line that continually approaches a what? Given curve. But, ooh, the suspense is killing me. Let's see what's on this next page.
Does not meet the.
But never. Does not meet it at any finite distance, okay? It means we can't define it's infinitely close, all right? It's what we call limiting parallel. Here's kind of a sketch. Well, you know what? I'm just going to decimals. We have one right here. If I look at this graph right here, this is just going to blow up, get bigger and bigger and bigger, but where does this appear to flatten out at? At 0. Do you think it's going to cross 0? I don't think so either, right? So, kids, I'm going to leave that stuff at that. I think we've got a great start on what we need, and